today with us from King's College in London, and he will talk about mixing time of random walk on the dynamical random cluster.
Okay, thanks a lot for Inés for the invitation. It's a pleasure to be speaking here for you. Today, everything we're going to talk about today is a joint work with Andrea Lelli, which was my former PhD student, and now works in industry. So what I'm going to talk about, let me start with a slightly general model, not too general, but a bit general, of a random walk moving on a changing graph, a graph that changes over time. And we're going to look afterwards in two specific cases of this general model. So the model is very simple. You start with a fixed graph. For us, it's going to be just a torus. It's a finite graph, torus of side length n, but could be any finite graph that you want. And then each edge of the graph will have either one of two states. It can be either open or closed. And then these states, the state of each edge, can change over time according to some dynamics and Markov chain on the space of configurations, on the space of 0, 1 to the number of edges. Right. And we denote by eta t of e, which is either 0 if the edge e is closed at time t, or 1 if the edge e is open at time t. Okay, so it's very a bit general model. And on top of this picture, this is going to be our environment. On top of this, we're going to put a walker which walks on this graph. So it starts at the origin, or in a general graph setting, you could say you start from some given vertex, and then the walker jumps at rate 1. It's in continuous time, so even the dynamics on the graph, we take it to be in continuous time. So the walker jumps at rate 1, so it has a Poisson clock of rate 1. When this clock rings, then what the walker does, it chooses a neighbor on the graph. So on the torus, it chooses one of the 2D neighbors, and then it checks whether the edge connecting itself to that neighbor is open at that time. If it is, it crosses the edge. If it's not open, then it stays in the same vertex and just wait its clock to ring again. That's what the walker does. And at the same time, the environment just evolves independently of the walker. And we denote by xt the position of the walker at time t. So just a few remarks. So if our environment process, so the evolution of eta t, the environment is a Markov chain, so is what we call the full system, the system composed of the environment and the walker. And the stationary distribution of the walker in the case of the torus is uniform. In the case of a general graph, it's just the stationary distribution of a random walk on that graph. Easy to see. But if you look at only the walker, then this may not be a Markov chain, right? You can just imagine that if the walker stays at the same vertex for a long time from the whole interval 0t for a very large time t, so you expect it to collect information about the environment that may lead you to believe that the walker stay put for a bit longer after time t, for example. We're going to look at a concrete case in a minute. And the object we want to study is the mixing time of the walker, or if you don't want to get messed with the possibility that the xt may not be a Markov chain, then we can just look at the mixing time of the full system, which is a Markov chain, because we're always going to look at the environment process as a Markov chain.
I have a question.
Go for it.
So when you say stationary distribution is uniform, I guess the uniform distribution is always stationary, but the chain is not always irreducible, right? It depends on what eta does.
That's right. That's right. So the uniform is the stationary distribution, but you may not converge to it, right? That's what it happens, right? Yeah, but you're right. In our case, we're not going to run into this problem. The environment process will be reducible in all configurations, and we have no problem with irreducibility. Okay. Good. So that's the general model. So the most simple example I could come up with of this is dynamical percolation for the environment. So the walker is always going to be doing the same thing. The only change is going to be, we're going to consider two environmental processes. The first is dynamical percolation. So the initial configuration is just percolation, just take each edge and independently declare it open with probability P, closed with probability 1 minus P at time 0. And then from that time on, the environment evolves as dynamical percolation. That is, each edge has its own Poisson clock of rate mu. Mu is the same for each edge. And mu here, it may depend on n. I'll address this in a minute. So it has a Poisson clock of rate mu. When this clock rings, then the edge refreshes itself. That is, it flips a coin, and with probability P, it becomes open. With probability 1 minus P, it becomes closed, independently of what it was before, and independently of all the other edges. Okay, with each edge just doing their own business and flipping themselves to open and close independently. And here, I always take P to be a constant, something that doesn't depend on n, the size of the torus, just some value. And I don't care about the value. I'll care a bit about the value, but not the specific value. But mu here, I see it as a function of n. And the interesting case is when mu goes to 0 with n. So the graph is changing slowly in continuous time. So the walker jumps at rate 1, but the edges refresh at a much lower rate. Okay, and this is actually the interesting case. If mu was independent of n, then it gets easy. Another way to put this is that I want to quantify the dependence on mu on the results. That's what I want to do. Okay, and the environment is in stationarity, right? So if I look at any edge at any time t, then the probability that that edge is open at time t is p, which is the same probability as time 0. So, and this will be common to both cases where I'm going to see both dynamical percolation and the next one. Okay, so let me tell you, before I move to the other model, which is the one that I'm going to concentrate on, let me tell you what's the conjecture for the dynamical percolation. What do we expect it to happen for the mixing time? So for any dimension, including dimension 1, we can split this into two cases initially, at least. So there is a subcritical case, P is more than PC, and PC here is just a critical probability for bond percolation on ZD. So it depends on the dimension. And if P is more than PC, we expect, or the conjecture, the mixing time is n squared over mu, is of order n squared over mu. So let me tell you why we expect this. And the idea is the following. So we're in the subcritical case here. So all clusters of open edges are small. And so typically the walker is confined to a cluster of size of order 1, right? And the walker, since mu is going to 0 with n, so no edge of this cluster refreshes, and while the walker is really moving everywhere inside this cluster. It's essentially mixing inside this finite cluster, this small cluster, before anything can happen in the boundary that allows the walker to do something different. And it takes time 1 over mu for the cluster to change, since the cluster has size of order 1. So what really happens at the walker, we can discretize time and look at this process in intervals of time of length of order 1 over mu. And what the walker is doing is just some kind of a random step of length 1 of order 1 in time 1 over mu. So we expect that any square such random steps should be enough to mix. Each one takes a 1 over mu, so this gives you the n squared over mu. So that's the overall, let's say, rough idea why this is a conjecture. On the other hand, if P is bigger than PC, then you now give rise to a big cluster. Since we are in a finite torus, it's a giant cluster of volume m to the d. Then you expect a different behavior. You expect the mixing time to be of order n squared plus 1 over mu. And the rough idea why this is the case is that the walker well, first it can start out of the giant cluster. Just suppose the probability all edges adjacent to the walker are closed at time 0. In this case, the walker has to wait time 1/mu to actually even get out of its initial position. And it actually takes time 1/mu for the walker to enter the giant cluster, the giant component. Then the walker can walk a lot in the giant component, and you can expect that the mixing time will be dominated by this amount of these steps where the walker really enters the giant and can walk a lot. And the simple calculation to see that actually the walker spends equal amount of time inside and outside the giant components. Right? It's going to spend like 1/mu, but it walks a lot in the giant. So we expect that any square steps inside the giant should be enough to mix. So this will require any square steps overall after you enter the giant, but it took you 1/mu to enter the giant. So you pay 1/mu to enter the giant, but then only more n square steps to actually mix in the whole torus. Okay. So that's the conjectures. Let me just say that the first conjecture is a theorem. So that was proved by myself, Yuval Perez, and Jeff Steiff in the old days, where I proved the n square over mu is an upper and lower bound that differ just by a multiplicative constant. That does not depend on n, does not depend on mu. That's what we proved. The second conjecture is almost a theorem. Right? So it's proved by Yuval Perez, Perlasus, and Jeff Steiff that this result is true for p large enough and with an extra polylog factor. So they show that the mixing time is at most n square plus 1/mu, but times a polylog term, polylog correction, and this holds for p large enough. They can actually quantify how large p needs to be for the results to hold. Hey, but that everything else is essentially open on this question. And there is also the critical case for which I'm not even going to make a conjecture. Yes, please.
Yeah. I missed that maybe. So the mu may depend on n, right? And in these conjectures, what is the? I mean, is there any hypothesis on this dependence on mu in these conjectures?
No, any mu.
Okay.
You can do that. It could be even exponentially small in n.
Okay. Okay. Thank you.
What's important here is that you really are starting from stationarity, because otherwise you could start with some, for example, you could start with all edges open at time 0, and then the random walk would mix in time n square if mu is so small before any edge can actually flip, and then n square is the mixing time.
Okay. Thank you.
Yeah, so, but everything else here is open. So it's still open to close the gap on the supercritical case, and the critical case is all open. The only thing that's known for the critical case is that n square over mu, as in the subcritical regime, is an upper bound on the mixing time for the critical case. That's the only thing that's known. For dynamical percolation, there are some other results. There are results on the complete graph, and there are some general upper bounds on the mixing time, which is where it's proved that for the torus, in the critical case, you have an upper bound of n square over mu. But I'm not going to mention much this result because I'm going to take a different direction here. So is there any question? Yes.
Yeah, yes, in this result by Perez, Souzy, and Steiff, I guess they might, if you had a polylog, you might start from an arbitrary configuration, right? For the edges.
That's right. That's right. You can they can get a kind of a nil quenched result for the environment in this sense. Yeah, you're right.
Okay, thank you.
Yeah. Great. Okay, so yeah, so what did we want to do here? So my goal with Andrea was to start to look at the case where the edges do not refresh independently of one another. So we started to see what we can do to analyze the mixed time of a random walk in a graph where the edges have some dependence when they refresh. So that was the case, and we took a concrete discrete model for the environment is just dynamical random cluster. So we start the environment in the random cluster model. So it's just a configuration of open and closed edge, where each open edge gets a weight P, each closed edge gets a weight 1 minus P, just like percolation. And we have an additional term Q for each connected component in your graph. And then you normalize everything by normalizing constant. Okay, so that's the initial configuration of open and closed edge. And the dynamics that we take is just Glauber dynamics in continuous time at rate mu. So each edge has a Poisson clock. When the clock of rate mu rings of an edge, then an edge updates its states according to Glauber dynamics. So it becomes open or closed according to the measure that's conditioned on the state of all the other edges. So don't need to know any of this, but I'm going to describe what the Glauber dynamic is for the random cluster. It's easy to describe. It's just the following. So whenever an edge chooses to refresh, so its clock rings, then the edge looks at its current configuration and it has to see whether it's a cut edge or not. So what's a cut edge? So I have an example here on the right. Each edge that's open, it's drawn in the picture. Each edge that's closed, it's not drawn, like this one here. So I'm not keeping it out of the picture. And an edge like this one is not, or let's go to, it is a cut edge. So an edge like this one is a cut edge if there is no path between the endpoints that do not use this edge. Right? So there is no path from here to there without passing through this edge. So an edge that's closed can also be a cut edge, and the same thing. You just need to see whether there is a path between the endpoints that do not use the edge, a path of open, an open path. Let me be clear. And since there is none, this is also a cut edge. And you see the edges that are not a cut edge, you can find a path between the endpoints that are not using the edge itself. For example, in this case, you can find a path down here, and then left, and then up, right? And you find the path between these two endpoints. Then when the clock of an edge rings, the edge sees whether it's a cut edge or not in the current configuration. If it's not a cut edge, then it becomes open with probability P, otherwise closed with the 1 minus P. And if it is a cut edge, then the probability of being open changes to P divided by P plus 1 minus PQ. That's this. Okay. So important thing here is that the decision on whether open or close, it really depends on the current configuration. And again, this is stationary. Right? We start with a random cluster. We choose a Glauber dynamics that has the random cluster as a stationary measure. So that for any T, the probability that the environment is equal to a given configuration, eta is just the random cluster measure. Okay. And the walker is just doing always the same thing. So just jump at rate 1 and choose a neighbor uniform at random on the torus and jumps there if the edge is open at that time. Okay, so let me tell you, yes, in the case Q equals 1 is just dynamical percolations. If Q is equal to 1, the extra term that we had in the measure for each connected component disappears, and you get back to dynamical percolation. Okay. So what are the results? So it's one of these cases where the results are very unsurprising. So we show that for any Q positive, it doesn't need to be bigger than 1, and any dimension, if P is small enough, and that's a bit of a difference, if P is small enough, then the mixing time is at most a constant and is square of mu. Okay, so it's like what we obtained for the subcritical dynamical percolation, but instead of being able to show this for all the subcritical regime, we require P to be small enough. We have also lower bounds for this, and the lower bounds are a bit more precise, but not too much. So if Q is at least 1, and again, the dimension is always n dimension, then we can show that for in the whole subcritical regime, the mixing time is at least n square over mu, and these C's are all different, of course. So NPC of Q here is there's the critical probability for percolation, the random cluster measure with parameter Q. Okay. If Q is smaller than 1, so between 0 and 1, then we know very little about the random cluster measure. We don't even know that there is a single phase transition. So things get more complicated to understand the environment. So the lower bound, again, holds the lower bound of constant n squared over mu, but requires P to be small enough. Is there any questions about these results? Okay, so my goal for the rest of the talk, so the results are unsurprising because the main important thing are the proofs. So my goal now is to give you the ideas of the proof.
Alexandre,
about. Yeah, go.
Let me maybe I don't remember if is that correct, but Q equals 0 is the uniform spanning tree, right?
Yeah, the limit.
Yeah,
yes.
And what happens in the uniform spanning tree? Things are different, are expected to be different.
It's a very good question, and the easiest answer that I have never thought about it. that's really the easiest answer I can give you. So if you ask me tomorrow, maybe I'll have an answer.
Okay, thank you.
So for us, we really require, we don't take any limit in the model. We just take Q is just bigger than 0. Okay, so let me give you the ideas of the proof, and I hope I will convey you at least the main aspects of the proof and the main different things that we have to care about in this proof. But to start, I'm gonna tell you an idea that was already used in dynamical percolation from us in our results. And the idea is the following. So let's see this sentence here. So if we look at the case of dynamical percolation, so edges are just changing their state independently of one another. As we observe the walker jumping, we collect information about the environment, right? We collect information that the edge across which the walker jumped is open. And this information remains there because, you know, the walker, we are in the subcritical regime, so the walker is confined to a small space. It's going to revisit this edge over and over again. And this information remains there until the edge refreshes. The moment the edge refreshes, then all dependence on that information are removed completely because the edge really becomes fresh, independent of anything that happened in the past. And this motivated us to introduce a third stage of an edge, which we call star. So the edge could be in 3 states now: 0 meaning closed, 1 meaning open, star. And the star meant that the edge was refreshed since the last time the walker visited it. And just for convenience, we always take the edge adjacent to the random walk not to be star. So those are always revealed. Right? So I have an example here to the right. I have a piece of the torus, and here I'm drawing things different. I'm drawing with a black line, say, open edge, with a red dotted line close the edge, and I'm not drawing an edge if it's star. And what you see here in the walker is this red square here. So if this edge down here decides to refresh, then it just disappears from the picture. It becomes star. If an edge adjacent to the walker like this one decides to refresh, then it would disappear from the picture, but since it's adjacent to the walker, I immediately flip a coin and reveal whether it's open or closed. And I put there the corresponding answer. Okay. And that's the state space we are looking at when we analyze dynamical percolation, this enlarged state space. An important thing is that if I look at a star edge, the probability that a star edge is actually open, this is just P, right? Just independent of whatever. And looking at this dynamics, we could define a regeneration time, which is the time where all edges adjacent to the walker are closed. This was just convenient to trap the walker somewhere to gain time. And all the other edges are all star. And that for us was a very beautiful regeneration time and very useful. So why is this useful? And I will try to tell you quickly why, because it really summarizes the proof for the dynamical percolation. It's used in our case for the random cluster. So if we are in origination time, so suppose this to the left here is origination time, so the edges around the walker are closed, all the others are star, then this following sequence of events happen all in time constant over mu and occur with positive probability. So first, nothing happens until one of these four edges open, right? Suppose it was the edge to the right. It doesn't need to be the edge to the right, but some of these four edges open, suppose it was to the right for the picture. At some point, the walker traverses it. And when the walker traverses it, I have to see what the three edges that were star are now, because they are adjacent to the walker, and suppose they are all closed. This happens with positive probability. If this happens, then the walker now can go back and forth in this edge here like crazy, because it has nothing else to do, and is waiting something to happen with this edge, some edge to refresh. There are 7 edges in this picture, and the probability that the middle one is the first one to refresh is just 1/7, it's just a constant. And with constant probability, close. And so that's the next step in the event. Let's assume that the middle edge is the edge that refresh, and it refresh close. And then the walker is either to the left or to the right of the edge. I'm not caring which side it is for the moment, but for the picture, it's to the right of the edge. And I'm waiting for the last event in this sequence to happen, which is that these 3 edges that are not adjacent to the walker refresh before the edge that are adjacent to the walker. And if this happens, they all get started into a back to origination time. Right? All this happens with positive probability and in time of constant over mu, because it involves just a constant number of edges. Okay. And what happens at the end of this? Well, the walker did 1 step to the right. Now it was in origination time, it ended in the origination time, and they did 1 step to the right. And it did 1 step to the right, or stayed put if in this step here, it actually fell on the left when the edge closed. Well, it took the step to the right because the right edge here was the first one to open among the ones adjacent to the walker. If it was the one above it, the walker would have taken a step upwards. Right? The picture would be just rotated. What I'm trying to say here is that between these 2 origination times, the walker just did 1 step of simple random walk. And when this happens, we call such a origination time a simple random walk moment. That is the moment the walker did a simple random walk step. Okay? And it happens with positive probability. So, and that's all the proof. I have something from Zoom in the middle of my slide, but I hope you can see everything without anything covering it. So the idea of the proof is we need n square simple random walk moments to mix, because those are simple random walk steps. But to get this number of simple random walk moments, you need n square origination times, since each one with positive probability is a simple random walk moment. And then they take time constant over mu. And this gives us a mixing time that's at the most n squared over mu. Okay? So that's a very rough idea. We still have to control more. But I think this summary of the proof gives us the main steps that we will need when building up the proof for the random cluster. Okay. So is there any questions up to here?
Yes. So the part you didn't sketch is the fact that regeneration time take at most times C over mu, right?
That's right. That's right.
Is it difficult or?
That's probably the most difficult part, but I can just tell you. So typically, the walker will be in a cluster of size of order 1, and if it is in such a cluster, then you believe that with positive probability, these edges will just start refreshing, trap the walker somewhere, and everything will get star. Okay. If you turn out to be in a large cluster, or you have a very large number of edges that are non-star, then the goal is to show that this number decreases, and to show that you have some super martingale argument that show that this number decreases. But if you turn out to be in a very large cluster, this has to be done in 2 steps. First, you wait a bit for the cluster to be broken into small clusters just due to dynamical percolation. Large clusters cannot survive for long. Okay? Then, since now you are in a smaller cluster, then the walker is trapped, and this time that the walker is trapped in a cluster that will have at the most size log of the big cluster that was initially, will give enough time for the other clusters that the walker cannot reach to refresh. So you have to control a bit these dynamics. That's what's involved in showing the initial time is constant over mu. Okay.
Thank you.
Yeah. Okay, but now let's think about the random cluster. Suppose we want to do this idea for the random cluster. What happens? I need to click. Yeah. So we run a little bit into problem because when an edge refreshes, then its state depends on the current configuration. So a star edge, if I just call it a star, I miss the meaning of what a star edge was, which would mean it was something I didn't know about. Right? I am completely independent of the past. So what we do is that when an edge refreshes, we do the following procedure. First, we sample a uniform 0-1 random variable, u, independent of everything else, just sample it. And down here, I'm just showing you the interval 0-1 for a sketch. And we look at the configuration. Right? If the edge is a cut edge, then we know it's open if u falls to the left of p over p plus 1 minus pq. But if the edge is not a cut edge, then it's actually open if u falls to the left of p. In either case, we know that if u falls to the left of p over p plus 1 minus pq, the edge is open regardless of whether it is a cut edge or not. Right? And if u falls to the right of p, then we know it's closed, regardless of it being a cut edge or not. So if u falls in either of these 2 intervals, highlighted intervals, then I call my update oblivious, because it doesn't depend on the current configuration, and it's only then that I call this update stars. Then I call that edge star. Okay? So it's trying to mimic this argument, but we need to be careful, because if u falls in the middle, then its state will depend on the other edge. So what I will have to do is I will actually have to go to the endpoints of the edge E that's refreshing and start exploring the cluster from each of these endpoints to determine whether the edge is a cut edge or not, to decide whether it's open or closed. And this means I may reveal edges that before I have marked as star. So that's the dynamic that we're doing now. So just a bit of a few remarks. So as before, we always keep the edges adjacent to the walker revealed. They are never star. If they do an oblivious update, we just look at what it is, whether u is in the left or the right of the highlighted intervals. Maybe I should have said this better. So if u falls in either of this interval and it's not the edge is not adjacent to the walker, then I don't look at whether u falls to the left or to the right. I don't look whether it's open or closed. So that the probability that a star edge is actually open is just the ratio. Right? It's just the length of the left highlighted area divided by the sum of the 2 highlighted areas. So important, that doesn't depend on the configuration. And then the probability that an update is actually oblivious is just the length of this, the unit of these highlighted areas in the interval. And important thing that we use, or one place where we use p being small enough, is that this probability goes to 1 as p goes to 0. 1 minus p is going to 1, and this term to the left is going to 0. So essentially, our environment for a small p is a perturbation of dynamical percolation. But okay, a perturbation that has unbounded dependence. Okay. So that's how we're doing, that's how we're implementing the star edge. So now I'm in a good point to start describing you how the proof goes, and it's just a coupling. So we have two copies of the system. We have a copy of environment plus Walker, and I put a star here to highlight that this is the enlarged environment where I have the star for believers updates.
I have a question.
Yes.
So in this thing, star edges can become non-star even if the random walk is far away. Is that correct?
That's right. That's correct.
Okay.
That's correct. Yes. So whenever an edge rings and it's not no believers update, it's not going to be star. It's going to see whether it's open or closed, and it will become either 1 or 0. And in this process, it may reveal other star edges as well, as it explores the two endpoints to see whether it's a cut edge or not. Okay. So yes, now to look at to start to control the mixing time, we're going to do a coupling strategy of the two copies of the full system. So copy of environment and Walker, and another copy of environment and Walker. And of course, we're going to say the mixing time is going to be T. If we establish a full coupling, that is, the two environments are equal everywhere and the Walkers are at the same vertex. So there are two components of this coupling. There is the coupling of the environment and the coupling of the Walkers. The coupling of the environment is the easiest, and I can describe it in one sentence, and it's here. So what it says is, if an edge is, suppose I just observe the first copy, and I'll try to construct the second copy as a deterministic, in a deterministic function of the first one. So if an edge in the first copy does a no believers update at time t, then what I do is I take the corresponding edge in the other copy, which is not really the same edge, but it's an edge from the point of view of the Walker. That is the edge phi t of E, where phi t is just a translation map that sends the Walker at position t, xt to xt hat. Right? So if, for example, if E, an edge to the right of the Walker does a no believers update at time t, then an edge to the right of the Walker in the second copy does a no believers update at time t. If the update is not a believers, then I really could even just do independently. I just can update the second copy in an independent fashion. I just do non-believers updates there, but this could review all the star edges. I could couple them. I could even not couple them. It doesn't really matter. Right? You can do whatever you prefer as long as it's a coupling. So that's the environment. So just some remarks. If I do not believers update, I couple the edge. So I help coupling the environment. And remember that if two edges, an edge in one environment and the corresponding edge in the second environment, are both star edges, and I turn out I have to reveal them, I can couple this revealment so that they are both either open or either closed. So they really couple the environments of believers updates. While non-believers updates, of course, could uncouple the environment. And as Hubert was questioning, we always have a density of non-star edges because the probability of doing non-believers update is just constant. It's maybe a small, but it's constant. So the idea of trying to replicate the origination time is not going to be useful here because it takes just exponential time in n to the d to get to origination time as we were describing for dynamical percolation. So they're going to do something different here. Some more remarks. So if in the two copies, the environment's coupled around the Walker, so imagine that around the Walker, a ball of some radius around each Walker, I have exactly the same picture for the environment, then I could make the Walkers do the same jumps, right? If one jumps to the right, I make the other one jumps to the right, and can couple the Walker in this way. And these I called identity coupling. So it's a second Walker copying what the first Walker is doing. This has one advantage because it doesn't change our map phi t. It keeps the distance between the Walkers the same. It doesn't change the map phi t. So it helps coupling the environments. On the other hand, identity coupling is simply useless because I have to, if I want to bring the Walkers together, remember that I have to bring the Walkers to the same position by some time t. And to do that, identity coupling doesn't help at all. But the moment I make the walkers do something different, they not copy one another, then I change the map phi t, and edge that were coupled could uncouple. So there is a bit of a game here going on that we have to control. Okay, but the coupling of the environment is always going to be as described. So let me describe now the coupling of the walkers, which is the most difficult one. So I'll try to just give you some ideas. So if there is something unclear, just please ask. So the idea is that we tessellate space and time. So this picture here, time is vertical, space is horizontal. We're going to tessellate this into box up to some time. I didn't put time. Okay. Well, next slide will be clear with when I stop this tessellation, but I'll do tessellation in space-time, and I'm going to say that a box is going to be good for me if, and the definition of good just regards the environment, if all the updates inside that box, that is in the space for all edges that are contained in the box and during the whole interval of the box, are oblivious. And I want that the star edge behaves somehow as subcritical percolation. That is, that the largest clusters, if the box has side L, I want in space, I wanted the largest clusters at most log L, and essentially that's all I want actually. So the idea here is that if a walker enters a good box, well, it's in a good situation because I have a lot of oblivious updates, so things are mostly independent, and it doesn't move too much. So I can control where it's going, or at least where it's not going. So it's not going far away. The idea here is the following. So when the walker enters a good box, I want to take these moments to help couple the environments because I'm doing oblivious updates everywhere. So I can help couple the environments this way. And I will want to attempt a simple random walk moment. So remember that good box, the percolation is subcritical, so the walkers are stuck into small boxes, small clusters. So you can imagine that it's going to eventually be trapped in a position where all edges around it are closed. Meanwhile, oblivious updates are happening everywhere in the box. So you get a situation where you are stuck in a vertex, and all large number of edges around you are all star. So that's a good moment for you to try a simple random walk moment. That sequence of events I described before that guarantees that the walker does a step of a simple random walk. So what we can show is that there is a positive probability the walker does a simple random walk moment when it enters a good box. Okay. The tricky bit here is that we know the box is good, so you need to find that the probability of doing a simple random walk moment is large, even conditioning on the box being good, where you are revealing things about the environment. But okay, that's mostly technical. It's feasible to do it when P is mono. The problem is what happens when the walker enters a bad box, right? So when the walker enters a bad box, then all hell breaks loose. You don't know what's going on in bad box. They're just bad. And what I would like to do is just do identity coupling and hope for the best. That is, I try to make the two walkers do the same jumps, because if I do this, then I at least guarantee that the distance between them does not increase in bad box, because otherwise it could increase in a dependent way, and could this even affect the previous good steps I did of simple random walk moments. So the hope is really this. That's to identity coupling and hope for the best. And we know that identity coupling is successful if it turns out the environment around the walkers is coupled. Right? No matter how bad the box is, if the environment is coupled, you can do identity coupling. So let me now give you an overall picture of how this is implemented. So the idea is that we want to prepare ourselves before bad boxes, so that identity coupling is likely to be successful. Actually, in our case, it will be successful. So how do we do this? We just observe whether boxes are good and bad during the whole space, but up to times some big constant n square over mu. Just observe all of them. That's the picture I'm drawing the left here. We tessellate up to this time, and we observe each box whether they are good or bad. And we are drawing in red the bad box. Then we start to look at the walker, which comes from the origin. We start to walk in this picture upwards. And as long as the walker is passing through good box, we try these simple random walk moments. Right? They are nice moments where we can try to do a smarter coupling. We can try to do a simple random walk coupling of the two copies of the walkers. This uncouples the environment, as I said, because the distance between the walkers change, but you are in good box, so everything is oblivious, so you recouple the environment and things can keep going. The problem is that when the walker starts seeing that in the horizon, in the future, it's approaching a bad box, and approaching just means in each bad box I can mark a region where whenever the walker enters this region, I start worrying myself about that bad box. Then the idea is when the walker enters this region, this protection zone around the bad box, I turn off the simple random walk moments. That is, the walker inside here is passing through good boxes, but I won't do a simple random walk coupling anymore with the other copy of the walker. I'm just going to do identity coupling. And why is just to give a chance for the environments to start coupling around the walker in preparation for the walker to enter the bad box. Right? So this annulus, not annulus, but this region that between the bad box and the region where I start to worrying about the walker approaching this bad box is enough for if the walker really enters this bad box, they may not even enter it, may just deviate it and pass to the right of it or to the left of it, and that's it. No problem happened. But if it does enter the bad box, this region is enough for the whole environment to be coupled around the walker in this whole region around the bad box. And note that I have to couple the environment not only the bad box, but also a little bit to the left and to the right here, a bit in the neighborhood, because the walker could enter and exit a bad box during the life of a bad box, but cannot. Once it enters a good box to the left, it cannot really go to the other one to the left, because then the environment is subcritical there. It's a good box at the end. Right? So that's a dynamic. So each time you enter these regions around each bad box, you're going to worry about it, and you start turning off your simple random walk coupling, resource to identity coupling, so that the environment is coupled and you survive the bad box. And you're going to play your game all the time. And this gives rise, of course, to a non-Markovian coupling, because I need to look at the future information, how the environment looks like in the future, to decide which coupling strategies to apply in the present. So that's a little bit technical detail. Okay, so let's see what else. So let's see how we complete the proof here. So I'm just skimming through this. And this is actually the last bit of the talk. So the proof completed in this way. So we let the walkers now do this coupling. So simple random walk coupling if you are in good box outside these protection zones, and identity coupling in the protection zones and bad boxes. And you do this up to half of the time we review the box. Okay, so there are two here. So we reviewed up to Cn square over mu, and we do it half of the time. And the argument is just a percolation argument. To actually do this in multiscale way, but well, you could do it any way you prefer. You just have to show that the number of good boxes outside even protection zones that you cross in this way will be of order n square. So each box, you'll see here to the left, you see each box in time is of order 1 over mu in time. So if you go for Cn square over 2 mu time, you are going to pass through n square boxes, and a constant fraction of those will be good outside protection zone, allowing you for n square simple random walk moments, allowing you for n square simple random walk couplings. Okay? This will allow, it's enough amount of steps to bring the two walkers together. Right? But the problem is that you review the environment, and the environment may not even be coupled at that time. And you need, what we do is from half of the time to the end of the time, so from Cn squared over 2 mu to Cn squared over mu, you just do identity coupling without revealing anything else from the environment. To just do identity coupling all the way. And the only thing that could go bad is if you had done a simple random walk coupling before this time, but you should not have, because there is something bad much in the future that you should have started to prepare yourself much earlier, and you didn't know because you didn't review after Cn squared step of mu. But this is such a large time that's very unlikely to happen. So if it's very large probability, identity coupling succeeds from the first half to the second half that you review, from Cn squared over mu. And if this happens, then we can show that you just couple everything. You couple the walker, you couple the environments, and you arrive at a mixing time. Otherwise, this fails with some positive probability, but fixed, then you just repeat. There's an independent number of experiments, and you are done with the mixing. So this is essentially the whole strategy to show that the mixing time is of order Cn squared over mu. Is just to give you some of the ideas. And okay, I've stopped the talk here. I'm happy to address any questions you have. Thank you.
Okay, thank you very much, Alexander. Any questions? Any further questions?
So does everything break down if the random walk you're considering is not symmetric, the underlying random walk? I mean, I guess there are several ways to define bias here, but
yes, okay, that may require some thought. Let's say if the walker is not, so say it has bounded jumps, then nothing should break. Okay? But if your walker has unbounded jumps, then maybe the dependence on mu have to be more carefully considered. But if it has bounded jumps, you just do the same kind of argument, but you have to just redefine what a simple random walk moment is. You have to come up with a more complicated.
But cannot there be some kind of trapping phenomenon? I don't know. For nearest neighbor with a bias, you can be trapped on the on kind of branches of the.
That's right, but the dynamic saves you, right?
Okay.
I mean, you have to see that we're really considering here subcritical, right? So it's quite crucial here that we look at P very small, and this argument does not really carry through to P that's supercritical, where you may see the trapping to be more important.
Alexander, Pablo here. So this is especially you are looking to forget the environment you have seen, right?
Yeah.
So what happens if you, instead of having percolation or random cluster model, dynamical, you have exclusion or some other conservative dynamics?
Yes, that's a very good question. I haven't thought about this. It certainly breaks, at least the idea of the star edge as we define it breaks. You'd have to maybe come up with a different notion of forgetting your environment. So the short answer is I haven't thought about this because mixing time is a bit delicate. Right? I mean, you have several ways to show decoupling of your environment if you have some conservative dynamics or some other interacting particle system that defines your environment. But for the mixing time, this can be quite complicated to see what an oblivious step or how to recover independence from previous steps of the walker is. So there are some nasty dependence of the walker with the environment. So this case can be quite complicated. I haven't yet thought about it.
Thank you.
So I have a question.
Yeah.
Yeah. So in principle, the couple particle environment is a Markov chain. So this question about mixing also makes sense for that couple, no?
Mm-hmm.
So can you say something about that?
Yes, but that's exactly what we did, right? So we get the mixing time of the couple environment and Markov and the walker. And in this case, if the mixing time, you could also talk about mixing time of just the walker. We have to define it properly, but you can talk about the mixing time of the walker alone, and they're the same. Both the full system and just the walker have the same mixing time.
Yeah. Okay.
Okay, it's not the case in the supercritical, but the subcritical. The thing is, the environment mixing time log n over mu, right? Or 1 over mu times log n. Right? And if you compare this with n squared over mu, the n squared over mu is much larger. So it just absorbs the mixing time of the environment. But in the supercritical, it may make a difference if you expect the walker to mix in time n squared plus 1 over mu. So then there you need to make a bit more of a distinction. But in the subcritical case, it's all the same.
Okay.
Yes, I have a question.
Yep.
So what happens in the critical case for just random flips for the percolation, not in the Glauber case?
Yes, so essentially nothing is known. I can tell you what we expect it to be somewhere in between the supercritical and subcritical, but it's even unclear to me how the dependence on mu will be. So I don't have much of a conjecture to state for the critical case.
Okay. Thanks.
Okay, if there are no more questions, let's thank Alexandre again. Thank you very much, and we'll meet next week.
Thank you. Thank you, everybody.
Thank you, Alexander.
Thank you. Bye.
Bye.